Welcome to ScaleUp University. Welcome to the course on designing data intensive applications. So this is the lecture 7 of module 1, and in this lecture we will be discussing software faults and systemic risk. So if we look at the lecture overview, like what this lecture is about, what we will be discussing in this lecture. So see, if we talk about software, it feels very reliable because code is deterministic in nature. Like let us suppose we have written the code. Now if we test it rigorously, then we know that, okay, it will behave as intended because code is deterministic. Whatever the code is written, it will behave like that. It will never happen that code is for something and when we are running it, something else is happening. It never happens. So the code is deterministic. And so the idea is that if we test it rigorously, we are very confident that, okay, software will work no matter what. So because the code is deterministic, software feels very reliable. And also machines, they execute instructions exactly. Like machines, they always execute instructions the same way. It is not like sometimes the instruction execution will be in a different way. It will not happen. So machines, they will execute instructions exactly, and hence softwares, they feel very reliable because no randomness or undeterministic behavior we can see in software systems. So if it works once, it should work again. So let us suppose a piece of code, if it is working, then it should work because there is no bug or error in the code. So that's why while in testing, like we test it, and if we see that, okay, the software is running fine, like the user acceptance testing we did, and if the software passes the user acceptance testing, we are very confident that, okay, now the software will work. We call it the software feels reliable. So given the same input and environment, a program will always produce the same output. But we have a hidden truth about software systems. So here is the hidden truth that we'll discuss about software systems. So software systems, they don't fail randomly, but collectively. So the idea is that when bug exists in software systems, so let us suppose a bug exists, then that bug, it exists in every deployed copy. So let us suppose we are following a redundant architecture wherein we are having multiple replicas of the node. Now multiple copies, like every deployed copy on different nodes will, the bug will migrate there. So if a bug is there, it it will exist in every deployed copy. And because of that, the failure will be systemic failure. Then it will not be a fault, rather it will be a failure, because if that bug migrates to all the nodes, entire system may collapse. So software bug, it can affect every node simultaneously. It can create systemic failure, and hence software faults can be systemic in nature, and it can be very dangerous. So unlike hardware faults, which are independent, see, hardware faults are independent because in hardware, if a component fails, it might affect that particular node. It cannot affect any other node. So hardware faults are independent and they are localized. So unlike hardware faults, software faults, they can very easily migrate, and hence they can lead to systemic failures. So software faults, they are often global and synchronized. And that's the problem with the software faults. So software faults, they lead to systemic failures. Software faults are correlated and reproducible, and it makes them capable of taking down the entire system at once. And hence software faults and can be very dangerous. And that is what we will discuss in this lecture. This lecture is all about software faults and systemic risk. And definitely you got a very good idea about the like what are software faults and how dangerous that can be. Like software faults, they can very easily migrate. So they are global and synchronized, and they can very easily lead to systemic failure. So that is what we will discuss in detail in this lecture. This lecture is about software faults and systemic risk. So if we look at the topics that we will cover, so in this lecture we will discuss software bugs as correlated failures, cascading failures, hidden coupling between components. Why are software faults harder than hardware faults? Testing limitations in distributed systems, systemic risk in software systems, the core engineering lesson. So all this we will discuss, all the topics we'll discuss in this lecture itself one by one. So this is the module 1, trade-offs in data systems architecture, lecture 7, software faults and systemic risk. And we are starting with the first topic of this lecture, software bugs as correlated failures. So what is a correlated failure? First, let us understand that. So a correlated failure occurs when multiple components they fail due to the same underlying cause. So if the same underlying cause it is responsible for the failure of multiple components, then it is a correlated failure. Let us look at an example. Let us suppose we have a bad deployment. Because of the bad deployment, it introduced a memory leak. So a bad deployment introduces a memory leak in the system. Now the idea is that this deployment it will be migrated to all the nodes, because we know that we maintain redundant copies, redundant nodes running the same code. So this deployment will be migrated to all the nodes. So memory leak will be introduced in all the nodes. So all instances will run the same code, and hence all instances will crash under the load because of the memory leak. So correlated failure, it is not random failure. Rather, it is systemic failure, because here the underlying cause is the same, that is the memory leak. Underlying cause is the bad deployment which introduced the memory leak, and this is the reason, and because of this reason all the nodes, all the multiple components they failed. So it led to a systemic failure. And if we contrast it with the hardware failure, if we contrast it with the hardware failure, so in hardware, disk A fails today. Okay, so in hardware, what happens is that let us suppose disk A fails today, then it has nothing to do with the disk B. Disk B may fail next month or some other time. So in hardware, the faults are independent in nature. They are independent events. But in software, on the other hand, let us suppose there is a bug. Now that bug it will trigger all the instances, because if the same copy of the code is running in all the three instances, for example, instance 1, instance 2, instance 3. So a small bug in the code, it will be migrated to all the instances. So in a software failure, all instances they behave incorrectly immediately. So software failures, they are global and synchronized, and hardware failures, they are localized. Let us look at some examples, some real world examples of software failures, or real world examples of correlated failures, wherein multiple components fail due to the same underlying cause. So infinite retry loops overwhelming downstream systems. So infinite retry loops is an example of a correlated failure. Misconfigured timeouts causing global cascading retries. Now see, the idea is that let us suppose if the timeouts are misconfigured, configured. So in a distributed environment, if a node is not getting a response, it might like keep on retrying because of the misconfigured timeouts. And any other node which is dependent on this node which is retrying, it might also get stuck. So here misconfigured timeout, it introduced a, a sort of a problem or a bug, and it migrated, because in distributed environment, these nodes or these software components, they are dependent on each other. So if one component, it is facing an issue, that issue gets migrated to all the other components which are dependent on this component. So we call it global cascading retries. Incorrect assumptions about input validation. So if we have incorrect assumptions about input validation, it can lead to correlated failure or a bad feature flag. So any bad feature integration, it will enable faulty logic everywhere. Let us suppose in the library, in the software library, a faulty logic is there, a bad feature is there. Now, whatever code which is importing that library, that fault, that faulty logic will get migrated. So it will lead to a software bug. So software bug, like they are correlated failures, and we can see that in all these examples, it is global in nature, wherein it is very easily getting migrated. It is not affecting just the individual node or individual component, rather it is also affecting the other nodes and other components. So it is affecting the entire system as a whole, and hence it is systemic in nature. So if we look into the key insights, so see, the idea is that we already saw that replication is very important, because replication, what it does is that it increases reliability for hardware faults. Because if we replicate hardware, so if any hardware is facing an issue, we can have a backup in place. But replication is dangerous for software bugs because it amplifies risk for software faults. Because we already saw that the software fault, it will migrate to all the replicas. So replication will amplify risk for software faults. And why is it so? Because if we talk about replica, they share the same code, same configuration, and same assumption. So there is a, like we are facing a replication paradox, wherein on one hand it is adding value in dealing with hardware faults, but on the other hand it is amplifying risk when it comes to dealing with software faults. So it is like a double edged sword. Replication. Cascading failures. So what is a cascading failure? So a cascading failure, it occurs when one component failure triggers failures in other components. So that is cascading. Cascading means, let us suppose a failure in one component, it led to the failures in other components. So cascading effect. So that's a cascading failure. So software faults, they are cascading in nature. Let us look at some example scenarios. If database slows down, so application, it will keep on retrying aggressively, because the application now it wants data. Now database, like now it is slowed down, so there is a lag or some latency is there, and application is sending request to the data, querying the database, but not getting the response. So it will keep on retrying aggressively. Now what will happen is that because of this aggressively retry, this retry traffic, it overloads database. Because of that, database will get confused. It will not be able to process the load, and the entire system will collapse. So a small bug or the fault in the database, like database, it's slowed down. It is very common. It might happen in a production environment, Because of the database slowdown, application, it faced an issue because it queried the database, it did not get the response, and aggressively it kept on retrying. Because of that, database, it was not able to handle the traffic overload, retry traffic overload, and the entire system collapsed. So it is an example of a cascading failure wherein the original fault was in the one component, that is a database, but it migrated, and it led to the, so the original problem was the minor slowdown, and it resulted in full outage. So cascading failure. So a minor slowdown of a database led to the full outage. So here, one of the main reason for that was the retry storms, and we should avoid it. So, so what is the idea? Like, see, clients, they keep on retrying on timeout, because let us suppose client, they sent a request to the server or any resource, they are waiting for the response. So timeout is the time they will wait, and once the time is out, like they, let us suppose timeout is 10 seconds, they will wait for 10 seconds, then they will retry. Once again, they will wait for 10 seconds and they will retry, and they'll keep on doing it. So every 10 seconds, the client will keep on sending the request on timeout. Now the problem is that, let us suppose if the server is down or any resource is down, and multiple clients, many clients are trying to access it simultaneously. And since it is down, or it is slow down, many clients will retry simultaneously. Because of that, retry load, it will multiply. And ultimately, we call it retry storms. The resource, for example, the database or the server, it will be exploded with a retry traffic, and it will not be able to handle it, and it will collapse. So retry storms can lead to system collapse. So in cascading failure, we have to also discuss feedback loops. So in software systems, we have positive feedback loops. So what positive feedback loop is, let us understand. So see, in software, what happens is that software often uses the positive feedback where a failure signals the system to work even harder. Like the idea is that, like in a software, multiple components, they are working and they're also interacting with each other. Now let us suppose the software receives a failure signal from any component. Now what it will do is, it will make it to work even harder to resolve that issue, and this will amplify the original stress. And that is what happened in earlier scenarios also. So wherein database slowdown was a failure signal, because application, it was trying to query the database, but it was unable to fetch the records or get the result. So database slowdown was a failure signal. Now the application, what it will do, it will work even harder. It will keep on retrying. So that is the positive feedback loop. So positive feedback loop can be very dangerous. So it can lead to cascading failure. So positive feedback loops in the software systems can lead to cascading failure, wherein any failure signal, the software will respond it more rigorously, leading to the collapse of the entire system. We also have something called as amplification effects or resource exhaustion. Now what it is, let us suppose a slowdown in one area, like disk input output, causes requests to pile up in memory. Because let us suppose disk input output gets slowed down. Now the incoming request, it will keep on piling up in the memory. Now what will happen is that RAM will get filled up, and operating system will end up spending most of the time in swapping memory to disk, because RAM is limited. So lots of requests got piled up. So most of the request, the operating system, it will save it in the disk. We call it swapping. which will even slow down the disk input output even more. Why? Because whatever data we wanted, it might be in the disk. So first we have to fetch it from the disk to the RAM and then make use of it. So this is the amplification effect. So amplification effect, because of resource constraints, let us suppose the RAM, there is already stress on the disk IO operation, disk input output operation. Because of that, lots of IO requests, they are piled up in the memory, and memory, it is like about to get overflowed. And because of that, operating system is swapping some of the IO requests to the hard disk. And because of that, even like the disk IO operation will even, it will get even more slow down. So that is the amplification effect. Emergent behavior. So what is emergent behavior? Sometimes a service becomes so overloaded that it spends 100% of its resources just managing the queue of incoming requests and 0% actual processing them. So that is the emergent behavior. So the idea is that sometimes a resource or a service, it becomes so occupied, so overloaded that 100% of the resources is just used in managing the request and not at all executing the request. So this makes small bugs massive outage. So in cascading failure, we got a realization that small bugs, even small bugs in the software systems, it can lead to massive outages. Hidden couplings between components. Now let us understand what is coupling in software systems. So coupling is like a sort of a interdependency. So coupling means components depend on assumptions about each other. Like dependency, coupling means dependency, means software components, they are dependent on each other. Now coupling, we can have explicit coupling, wherein we can have software systems, they are dependent on some API contracts, schema dependencies. We call it explicit coupling, which is visible, which we can feel it, which we can sense it, explicit coupling. And we also have hidden coupling, and this is very important, and this is very dangerous also. And what is hidden coupling? So see, the idea is that software systems now in the components, they, there are many assumptions are there, like timing assumptions. And what is the assumption? Like, let us suppose a component is dependent on another component in a way that it assumes that the data fetching component will fetch the data in 5 seconds. And what if it does not fetch the data in 5 seconds? So there are many assumptions. So in a software system, many components, they are interacting with each other, and there are many assumptions related to timing, load assumptions, retry behaviors, and implicit data invariants. So these are hidden coupling. Now see, the idea is that explicit coupling, it is visible to us, and with the, like, we can, like, via code, we can control it. We can control the explicit coupling via code. For example, let us suppose our software system is dependent on a third party API. Now, if the endpoint, it gets altered, we can change it in the code. Or any schema dependency, we can make changes in the schema, like some code, and we can work it out. So that is the explicit coupling. But hidden coupling is something which is invisible in the code, and hence it is very dangerous. Because see, the idea is that, let us suppose you have a perfect code, like you have written a code, like you have coded the software system, all the components of it, and in the lab, it is working perfectly fine. But the same software, when it is deployed, when it is in the production, you will start seeing s- so many faults. So those faults are not because of the any bug in the code, but rather because of the deployment. Because in the production, the software will come across so many unhandled scenarios or unseen scenarios, like the traffic. So the idea is hidden coupling. It is undocumented. It is invisible in the code. It emerges under load. So when your software, it is in the production and under heavy load, because under heavy load you will see many resources, many lag. You will start experiencing that lag you will never see in the lab. So when you're testing your software in the lab, there will be no such lags, so no latencies. But under heavy load in the production, the same software will start seeing so many load latencies. So all your timing assumption will fail. Because of that, the synchronization, it will fail. So hidden coupling appears only in rare conditions. So most major outages are caused by interactions, not individual failures. So this is very important observation. So in software systems, let us suppose you did a very rigorous testing and the software passed all the tests. Still, it can fail in the production because of hidden coupling, because that software will be subjected to heavy load, and in that there might be synchronization problem. So the problem will be with the interactions among the components. That will be the main problem for the systemic failure in the software system, not individual failures. So let us look at an example of a hidden coupling. Example of hidden coupling. So we have a service A. It assumes service B will respond in 100 millisecond, and we have service B which assumes service C is available. Now let us suppose service C slows down. Since service B is dependent on service C, so if service C slows down, what will happen is B will slow down. And since B slow down, the timing assumption of 100 millisecond, it will go wrong. So service A will keep on retrying. So instead of sending one request, it will send three requests, for example, because service B slow down. So service A times out and it will keep on retrying. So multiple requests it will send and the system will destabilize, the synchronization problem. So here the thing is that no component is wrong, because see, service A is perfectly fine. If you talk about the code, no component is wrong. Nothing is wrong with service A, service B, service C in terms of code. There is no bug. But service C slowed down, because not because of any bug, but because of the real world production environment, because of some load constraints. Because of that, service B slowed down. Because of that, service A, it was forced to do the retry storm, because the timing assumption went wrong. And because of the retry storm, service B, it was overloaded with retry requests, and the system might destabilize and it might fall. So no component is wrong, but the system, it collapses because of wrong assumptions, wrong timing assumptions, wrong load assumptions, retry behaviors, and implicit data invariants. And that is the hidden coupling. And this is something very important. So when we are designing software systems and when we are designing data intensive applications, because that application will be a software only, we have to give special emphasis to hidden coupling, because hidden coupling can be very dangerous. Why are software faults harder than hardware faults? So if we talk about hardware faults, they are random, they are independent, they're isolated, they're detectable often, and they're replaceable. Because see, hardware fault, if you talk about, any particular component will get failed, like that will be the fault, and it will be random in nature. It will be independent. Like a disk fault has nothing to do with any other hardware fault. Like it will be independent event. It will be isolated. Like very easily we can isolate a hardware fault. Let us suppose a disk, it is facing a issue. We can easily migrate, or easily we can go for a backup disk, and we can isolate this disk with problems. So hardware faults, we can isolate it. It is detectable and it is replaceable. We can replace it. But if it, on the other hand, if we talk about software faults, they are systemic. They are not random. Rather, they are systemic. They are systematic. They are correlated. They are hidden until triggered. They are reproducible. Like they are global. They are synchronized, and they often triggered by rare timing or scale conditions. When we try to scale software systems, we will encounter software faults. So the core problem is hardware faults are uncertain, they're probabilistic in nature. All of a sudden, the database might stop working because of some hardware fault, some power outage, or some other issue. But software faults are logical, and logic they logical errors they don't degrade gracefully. They can violate invariants immediately, and they can corrupt data before detection. So logical errors can be very dangerous because logical errors they can very easily spread out. Because of that, systems will not be able to degrade gracefully. Because the logical errors can very easily spread out, they can migrate. It can violate invariants immediately, and they can corrupt data before detection because very quickly they can migrate. If we look at one example of a race condition, so let us suppose I have a resource. So two threads, thread 1 and thread 2, they are trying to write simultaneously. So two writes occur simultaneously. Now, if locking assumption is incorrect, then data invariant will get violated because if two threads they're trying to access the same resource, so if locking assumptions are wrong, then very easily they can corrupt the data, like data invariant will get violated. So the thing is that, see, in the lab or in the development environment, you might not face this race condition, but the same system which is working on a development environment, it can very easily get failed under production concurrency because race condition it appear once every million operations, and race conditions are hard to detect, hard to reproduce, and hard to debug. Testing limitations in distributed systems. Okay, so why testing is inefficient or insufficient? Okay, so in distributed systems, testing is insufficient. See, testing is an essential safety net, but in the world of complex distributed systems, it is a statistical filter, not a guarantee of correctness. Because see, testing has to be a guarantee of correctness, but unfortunately, in distributed systems, testing is not a guarantee of correctness. There are testing limitations. And what are those testing limitations? So in distributed systems, there can be massive state spaces. So too many combinations, and we cannot test all those combinations. So the number of possible configurations and situations in complex distributed systems, it can grow exponentially, and it can even exceed our ability to simulate it. And there is no way we can simulate all the state spaces. And that is the testing limitations in distributed systems we are talking about. Non-deterministic timing. See, in production environment, the timing can be very uncertain. It can be very probabilistic in nature, and we cannot simulate it. So distributed systems in production environment, they are prone to non-deterministic timing, and we cannot test non-deterministic timing. So that is the testing limitations in distributed systems. And non-deterministic timing, one of the very good example of it is the delay. It may vary. Network variability. So network variability is something which is very common in distributed systems because distributed systems they are connected, and in real world in production environment network variability is very common, wherein we can see packet losses and latency spikes, and this we cannot test. So that is the testing limitation. Concurrency interleavings, that's the race conditions. So race conditions we can encounter. in production environment in distributed systems, and we cannot test it also. So in complex distributed systems, it is mathematically impossible to test all states. We cannot test all states. It's mathematically impossible. Now, what is the problem with traditional testing? So, in traditional testing, like if we talk about, we do something called as unit testing. So, in unit testing, we isolate logic and we ignore system context. So, in unit testing, every component we test it independently and we do not treat it the system as a whole. Integration test. Okay, so what is the problem with unit testing is that they cannot catch failures that emerge from the interaction of two services, because unit testing, it consider components independently. So when components they interact, certain issues might arise. So unit testing will not consider that. So that's the problem with unit testing. Now what's the problem with integration testing? So integration test, they simulate limited happy path scenarios. They cannot simulate all possible scenarios. So that's a problem. What's the problem with staging environments? So basically, while testing, we will be staging environment in a very smaller scale, and we'll be making use of different hardware and different data for testing. But in the production environment, if we take a complex distributed system, the scale will be huge. Hardware use will be different. Data generated will be different. So that is why we will be not be able to simulate staging environment also. And rare timing bugs. See, there are certain bugs which will only appear when a queue reaches 1 million items or a table hits 1 billion rows. And we rarely simulate this in staging because it is too expensive or slow. So rare timing bugs, they don't appear under low load or controlled conditions. They will appear only in the wild conditions, only in the production environment. We now will discuss Heisenberg bugs. So what are Heisenberg bugs? Heisenberg bugs are the bugs that disappear when observed. So a Heisenberg is a bug that seems to disappear or change its behavior when you attempt to study it. And it is named after the Heisenberg uncertainty principle. So Heisenberg is a special type of bug in software systems which disappears or which try to disappear when we start observing it. So bugs that disappear when observed, bugs that depend on precise timing, and bugs that appear only under high load conditions. So Heisenberg, they are special kind of bugs which are not inherent in the software system, which is not because of any problem with the code. Because any problem with the code, very easily we can observe it, we can debug it, but it is because of the scale of the distributed system. So these bugs, they appear under high load conditions. So when your complex distributed system, it is subjected to high load. So the application, the data intensive application, it might encounter Hazen bugs. So these Hazen bugs, they are usually tied to timing. When you add logging or debugging to find the bug, you slow down the execution. Because see, what happens is that Hazen bugs, when you try to debug or when you try to go deep, you will apply either debugging or logging. So with that, you are slowing down the execution. And this slight latency or slowdown in the execution will disappear this bug. This slight change in timing might prevent the race condition from occurring, making the bug vanish. And hence the name is given Hazen bug, because these bugs, we can experience it, but when we try to debug it, it disappears. Because when we try to debug, what is happening is that we are trying to slow down the system. And because of that, the race condition might vanish, go away, and the bug will go away. So Hazen bugs, we can only observe, feel it under high load conditions. So what key lessons we can take away is that while you are designing data intensive applications, don't rely on testing done in the development environment. Production is the ultimate test environment. This is a very important learning. Production is the ultimate test environment. So at scale, how system behaves, that is the real test. Because at scale, rare edge cases you will see. Rare edge cases become common occurrences. Timing windows widen, exposing races. Load patterns differ dramatically. Real user behavior is not equal to synthetic test. So real user behavior, it differs from synthetic test. So that is why we have chaos engineering. That is why failure injection is practiced. And that is why observability is critical. So when we are designing data intensive applications, we have to test it in the production. That is the ultimate real test. And we have to consider chaos engineering, failure injections, and observability. Because data intensive application is distributed in nature. So we cannot test it in a traditional way. Systemic risk in software systems. So systemic risk, it means a small defect can threaten the entire system. So systemic risk means a small defect can threaten the entire system. Now, what are the causes of systemic risk? Shared code base. So see, the idea is that if a bug exists in a common library, then it is not just about one app that is vulnerable. It is the every service that imports that library will get affected. So a code base which is faulty, which has bug, if it is shared across multiple instances, then it can lead to a systemic risk because it can lead to the collapse of the entire system. So systemic risk means a small defect which can threaten the entire system. So shared code base can be one of the way wherein we can threaten the entire system. Shared configuration. So see, modern systems, they often use centralized configurations. So a single incorrect misconfiguration like timeout value or a typo in a database URL, it can get pushed to 1000 services, 1000 servers in seconds, killing them all instantly. Because so here shared configuration means centralized configuration, and that shared configuration can affect hundreds or thousands of nodes simultaneously, and a small mistake in the configuration might lead to the system failure. Shared infrastructure. Multiple independent services, they often run on the same physical hardware. Now let us suppose your distributed system is making use of shared infrastructure. Any problem with this infrastructure, your entire system might collapse. Shared assumptions. So if every developer assumes the database will always respond in under 500 milliseconds, and the database suddenly takes 600 milliseconds, so every assumption is wrong. So every service may simultaneously time out and crash. So shared assumptions. So these are like some very common scenarios, some common causes of systemic risk wherein a small defect, because a small wrong assumption can lead to the system collapse. A small misconfiguration can lead to the system collapse. A very small bug in the code might lead to the system collapse. And what are the mitigation strategies, like how we can avoid systemic risk? So what we should do is gradual rollouts. So gradual rollouts means, let us suppose you made 10 changes. So don't like introduce those 10 changes in the production environment at once. First, you introduce one or two changes, test it in the production environment, then introduce third change, fourth change, fifth change, like that. So gradual rollout. is very important. So gradual rollout will mitigate systemic risk in software systems. Canary deployments matter. So canary deployment means, let us suppose you integrated a new feature or you did some upgradation. Now instead of giving it to the entire audience, entire user base, you deploy it to a small chunk of the user base. So you deploy the new code or new feature updation to a tiny fraction of users, example 1%. You monitor that 1% for errors. If it fails, only 1% will get affected. And if the canary is healthy, then you roll it out to 10%, then 50%, then 100%. This transforms a systemic risk into a contained risk. So canary deployment is very important. So the idea is very clear. So let us suppose you made some very significant changes. Now, instead of introducing those significant changes to all the users, you introduce it to 5% of the user. You test it in the production environment with the 5% of the user. If you feel like everything is correct, it is able to bear the load of 5%, then increase the load. Then introduce that feature upgradation to 50% of the user base, and then 100%. So in this way, you will avoid systemic risk. And because let us suppose you introduce the new feature to 25% of the user base and your system crashed. So only 25% of your user base will get affected. That's the idea. You should go for feature flags. So the idea of feature flag is that in the code, you should have something like, if feature is enabled, then run the new logic. Otherwise, run the old logic. So let us suppose you integrated a new feature and you found that because of the new feature, the system is collapsing. Then very easily you can flag off the feature, because a small configuration, you flag off the feature, code will automatically take care of that, because in the code the logic is written, if feature flag is off, continue with the previous version. So no need to rewrite the code. So that is very smart move. So feature flag is very important. Isolation boundaries matter. So we saw systemic risk in software systems and how we can mitigate it, the causes of it and how we can deal with it. The core engineering lesson. See, now a very big lesson we should learn is, we cannot eliminate software bugs. So you cannot eliminate software bugs, because in the production environment under heavy load, the software will encounter so many bugs, so many race conditions you might never have imagined. So you cannot eliminate software bugs. Rather, what we can do is that we can design systems that can limit blast radius. And how we can limit blast radius? Via canary deployments. Because we already saw that instead of deploying the new changes or introducing the new changes to 100% of your user base, you introduce it to the 1%, then 5%, then 10%. So that is the canary deployment. We should make use of cellular architecture, wherein we are dividing our infrastructure into cells, like customer group A, customer group B. Now, any problem with the hardware, only customer group A will get affected. Only that cell will get affected. So that is the limiting the blast radius. Database sharding. It means we have to split data across multiple databases, so that a corruption bug or a query of death only takes down a portion of your data, not the entire data. So database sharding is very important. In this way, we can limit the blast radius. We can also isolate failures. We can isolate failures via timeouts and circuit breakers. Let us suppose a software component is not responding. We can introduce timeouts, so that we are not waiting for the resource forever. After a point of time, timeout will occur. Then we can gracefully degrade. So With timeouts and circuit breakers, we can isolate failures, software failures I'm talking about. We should avoid tight coupling. And how we can avoid tight coupling is via asynchronous communication and dependency minimization. We should minimize the dependency and we should go for asynchronous communication. And what is asynchronous communication is that you send a request. Now you will not wait for the response. Rather, you will busy in doing other work. And once the response is available, you will get notified and you can make use of it. In this way, you are not getting stuck. And that is very powerful. Asynchronous communication is very powerful in software design because software components, if they are just waiting and waiting and waiting for the resources or waiting for the responses, that is very bad. Rather, asynchronous communication that enables software components that, okay, you sent a request, now don't wait for the response. Rather, you keep yourself busy in doing some other task. And once the response is available, you will get to know and you can make use of that response. So we can avoid tight coupling via asynchronous communication and dependency minimization. We should also go for degrade gracefully. Like fallback logic should be there and priority shedding should be there. And most importantly, we should monitor aggressively. So we should look for golden signals. And what are the golden signals? We should monitor latency, traffic, errors, and saturation. And we should prefer observability over monitoring. So both are different. Observability is different, monitoring is different. Monitoring will tell you that something is wrong, and observability, that logs, distributed traces tell you why it is wrong. And that is more important. So observability will give you the reason for the failure. Monitoring, like you are monitoring the system. If something is wrong, monitoring will just tell you that something is wrong. It will just monitor something is wrong. But observability, it is keeping track of all the logs, distributed traces, and it will also tell you, help you in identifying why it is wrong. So the reason for the failure. And we should also go for automated alerts. So now the idea is very clear. The core engineering lesson we should take away. Like, see, software faults is something which we cannot eliminate. So what we should do rather is that when you are designing data intensive applications, you should limit the blast radius via canary deployment, following cellular architecture and database sharding. While designing the data intensive applications which is distributed in nature, you should isolate failures by introducing timeouts and circuit breakers. You should avoid tight coupling by introducing asynchronous communication and dependency minimization. Your data intensive application, which is distributed in nature, should degrade gracefully. And how it can degrade gracefully under software faults is fallback logic and priority shedding. And we should monitor aggressively our data intensive applications. We should monitor it. We should monitor the golden signals, the latency, traffic, errors, and saturation. And we should prefer observability over monitoring. So finally, we completed this lecture. In this lecture, we saw that software faults are correlated failures. Cascading failures amplify small issues. Hidden coupling creates systemic risk. Software faults are harder than hardware faults. Testing cannot prove distributed correctness. We saw the distributed systems, we cannot test it perfectly. Testing a complex distributed system will not guarantee correctness. So the core insight which you can take while designing data intensive application is the most dangerous failures are not random hardware crashes. They are logical mistakes which gets amplified by scale. So I hope you got a very good understanding of the concepts that we discussed in this lecture. So do subscribe to our YouTube channel, ScaleUp University, for more such interesting courses and lectures. Thanks for watching. Thanks for your time.